Problem number 10. Approximate the value of each irrational number. The square root of 39. Now, in order to approximate the value, we can certainly put this into the calculator and get a value and round it. But that's not what we practiced in class. We practiced being able to get an approximate value by approximating the distance the square root of 39 is between its nearest perfect square roots. So its nearest perfect square roots would be the square root of 36, which we know to be 6, and the square root of 49, which we know to be 7. So the value of the square root of 39 is going to be between 6 and 7. Well, now we want to know more accurately what its decimal value might be. So we know its value is going to be greater than 6, and it has to be less than 7, so it's going to be 6 point something. And now in order to approximate its decimal value, we're going to take our 39 value and subtract from it, 36. And 39 minus 36 gives us 3. Then we're going to take our 49 value and subtract from that 36. That essentially gives us the part of our distance between those two perfect squares that represents our decimal value. So 49 minus 36 is 13. And when we divide 3 by 13, we get 0.23. So our approximate value of this irrational number is 6.23. Number 11. Number 11 is the square root of 225, and since we recognize that to be a perfect square, we should be noticing right away that it's not truly an irrational number, but rather it's rational since it simplifies to an integer. Its solution is 15. Number 12, we see the 1.21 in the radicand. So the square root of 1.21. And we should notice right away that 121 is a perfect square. So again, since we have a perfect square inside the radicand, we're going to actually end up with a rational number. 121 would be 11 times 11. Now, obviously, 11 times 11 gives us positive 121 and not 1.21, but it's still going to be the combination of multiplying 11 times 11 that gives us 121, but we need to account for the decimals in the solution. Now, our understanding of multiplying decimals, if we have 2 decimals in our solution, that means that we multiplied by 2 decimal places. The only way that we can multiply by 2 decimal places and still be multiplying by the same number, which is what we consider a squared value, is for both of our values to have the decimal place move over 1 position. So that's going to give us 1.1 times 1.1. And if you checked your solution, you would find that 1.1 times 1.1 is 1.21. Well, that means that the solution to the square root of 1.21 is in fact 1.1. Number 13. Number 13 gives us the value 546 million. And we're asked to write this in scientific notation. Now, in order for us to write it in scientific notation, we need to move the decimal from the end here all the way down so that we end up with a leading term that is between 1 and 1 and 9. And so I'm going to put the decimal right after the 5, which gives me 5.46. And 5.46 is a value between 1 and 9 times 10. Now, in order for us to figure out what power we're going to give to this 10, we need to count how many times we needed to move that decimal place to get it from the end of 546 million all the way over to between that 5 and 4. And so I realize I have 3 zeros plus 3 more zeros is 6 zeros, plus the 2 places that account for my 6 and 4. And so that would be 8 total shifts to the left. So I'm multiplying by 10 to the 8th power. Number 14. Now we have 0.00000034. So again, I need to figure out what I'm going to do to move that decimal all the way down so that I end up with a value between 1 and 10, or 1 and 9. That's going to be 3.4 times 10. Each time I move that decimal, it's a negative power. So it's going to be negative 1, 2, 3, 4, 5, 6, 7. So 10 to the negative 7th power. Now, an easier way to keep track of whether or not I'm going to have a positive power or a negative power, if it's a really big number, like in problem 13, it's going to have a positive power. If it's a really small number, like in problem 14, it's going to have a negative power. Now, this makes sense logically when we're thinking of fractions too, because if it's a positive power, then that's going to multiply by the term in front of the 10, and we end up with a whole number that's greater than 1. If it's a negative power, we would apply our exponent rule that says to kick that 10 to the negative 7th down into the basement. And so I would end up with 3.4 times 10 to the, divided by 10 to the 7th power. And when I divide by a value that large, it's going to give me a very small fraction of an answer. Problem number 15. 5.457e 10. Now we should remember from class that the e basically means times 10, and the value following the e is the power. So this is a quick, easy rewrite. 5.457 times 10 to replace the e and raise the power to the 10th power. Number 16, 8.22 e negative 10. So again, same process, a quick rewrite. 8.22 times 10, and now we're going to have a negative 10th power. Number 17. 183.4 times 10 to the negative 5th. Now this type of problem is what I like to consider that almost scientific notation problem. We recognize that we are multiplying by a base of 10 with a power, but the term in front of the base 10 is not a value between 1 and 9. So we still need to adjust it a little bit to make sure that it is in true scientific notation form. And we do that by moving the decimal to the left 2 places, which will give me 1.834 4 times 10. Now, anytime we move the decimal to the left, that causes our power to increase. So we will have 2 decimals to the left. My power currently is -5. It's going to increase by 2. And -5 plus 2 is -3. So my solution, 1.834 times 10 to the -3rd power. Number 18. Zero 0.004 times 10 to the 15th power. Now again, this is one of those ones that is almost scientific notation. In order to make it a scientific notation, we need our leading term to be between 1 and 9. So I'm going to move the decimal 1, 2, 3 places. If the decimal is now to the right of the 4, I have 4 times 10. And in our previous problem, we moved the decimal to the left. That caused our powers to increase. In this problem, we moved our decimal to the right 3 places. So we are going to subtract 3 from our power. 15 minus 3 is 12. So our solution is 4 times 10 to the 12th power. Problem number 19, we're now taking scientific notation and writing it out in standard notation. 9.7 times 10 to the -5th power. Right away, I know just from looking at that -5 in the power that we're dealing with a really small value. And so when I start to ask myself, which direction do I move the decimal? If I move the decimal to the right, even 1 space, I go from 9.7 to 97. Well, 97 is not a small value. And so I know right away that I don't need to move to the right. I need to move to the left. So I'm going to move the decimal to the left, and we accomplish that by first writing out our term 97. And I remember where the decimal starts. I'm going to move 1 space over, 2 spaces over, 3 spaces over, 4 spaces over, 5 spaces over. That's where my new decimal term goes. For each one of these loops, there needs to be substituted a value of 0. And then I told you in class I like to see a 0 before the decimal place, just so that it helps me to know for sure where your decimal place should be. So 0.0000097 is your solution to problem 19. Number 20. 6.12 times 10 to the 6th power. Now 6.12 times 10 to the 6th power, I see a power of 6, which tells me I'm going to have a really large number. So I'm going to start with my 612, and remember my decimal was between the 6 and the 1, so if I move to the right 1, 2, 3, 4, 5, 6 places, my new decimal is going to be right there, and we fill in again the loops with zeros and rewrite our number. 612 with 4 zeros following it. 1, 2, 3, 4. Now that I'm dealing with a large term, we're going to add our commas so that our notation looks cleaner. And I can go ahead and put my decimal at the end just to make sure that I know where it's at. So we end up with 6,120,000. Problem number 21. 1.2 times 10 to the negative first power. Again, a negative power means that I'm dealing with a small number. So in this instance, again, my decimal is going to move. It's going to move to the left one place because our negative first power. And so I'm going to end up with 0.12. Problem 22. 0.04 times 10 to the 6th power. Multiplying by 10 to the 6th power is going to create a larger term. Remember, the term is still equivalent. It's just going to make my my decimal answer here look like a larger value because that power is going to shift the decimal over. So for this particular problem, we're going to move the decimal to the right 6 places. So we end up with 1, 2, 3, 4, 5, 6. My decimal's going there, and we fill in each loop with a 0. So I see that I'm left with 40,000, which is 40,000.